Today, we're diving into the command pattern, building a system that lets us map actions to buttons, replay sequences, and even detect combos. It's not just code, it's architecture for smarter input. The command pattern is a behavioral design pattern that turns actions into objects. It lets us encapsulate a request, say button press, as a standalone command, making it reusable, queuable, undoable, or replayable. Most importantly, it decouples who issues the command from who carries it out. In game development, the command pattern unlocks real power. It allows you to remap input without changing your core logic. It enables features like action replay, combo moves, undo systems, and more. All of this while keeping your architecture clean, testable, and scalable. At the heart of the command pattern is the command interface, which defines a single method, execute. Each concrete command implements this interface and connects to a receiver, the object that knows how to perform the action. The invoker holds the command and decides when to call it. Finally, the client sets everything up. It creates the command, connects it to a receiver, and assigns it to the invoker. This way, logic, triggering, and actions all stay cleanly separated. Let's begin building our command pattern system by isolating animation logic into a reusable component called the animation manager. This class is responsible for cleanly playing animations using hash clip names, a much cleaner alternative to using string names scattered across the code base. Here at the top, we declare static animation hashes, idle, jump, attack, and combo. This lets us reference animations by a fast integer key rather than a fragile string. Think of this as compiling animation names into IDs, faster and less error-prone. Next, in awake, we get a reference to the animator, then cache the length of each animation clip using its hash. That means any system, like a command or combo tracker, can later ask how long is this animation, without parsing or searching clips every time. The method playClip uses Unity's crossfade, which allows for a smooth transition between animations. We pass in the hash, and the system handles the blend automatically. This is useful when chaining commands or responding to fast input. Finally, getClipLength lets other parts of the system retrieve clip duration by hash. That's going to be critical when we implement replay and combo logic. Here we define the iCommand interface. It includes a single method execute, which returns a task. Now this return type isn't strictly necessary for the command pattern. Many implementations just return void, but in our case, returning a task allows us to handle asynchronous operations, like waiting for an animation to complete, without blocking the main thread. This gives us room to do things like replay sequences, chain commands with delays, or await input combos, all without freezing the game or building workarounds. Here's our first concrete command, animation command. It implements iCommand, which means it must provide an execute method. This command's purpose is simple. Play an animation clip, wait for it to finish, then return to idle. We inject two dependencies through the constructor, an animation manager which knows how to play clips, and a clip hash, which tells what to play. This makes the command fully reusable. It could be a jump, an attack, or even a combo starter. Inside execute, we start by playing the animation. Then we use something called awaitable, wait for seconds async, a Unity-specific utility that lets us asynchronously wait for the animation's duration. Once it finishes, we play the idle clip to reset the character. Now, unlike tasks that delay, awaitable is purpose-built for Unity. It plays nicely with the game loop and is frame safe and memory efficient, perfect for gameplay scenarios like this one. So what we've built here is a self-contained, asynchronous, reusable animation command, clean, testable, and ready for replay or combo logic later on. Now let's take our command one step further. Here we have animation with VFX command, which plays an animation and a visual effect, like a sword trail, an explosion, or a magical burst. This class still implements iCommand, and we inject the same animation manager and animation hash. But we also pass in a reference to a particle system for the visual effect. In execute, we trigger the VFX using vfx.play. Then play the animation just as before. We wait for the animation's duration using awaitable, wait for seconds async, and finally return to idle. What makes this elegant is how naturally it fits into our existing system. We didn't need to change any core logic, we just introduced a new command. Whether we're adding VFX, audio, or even camera shake, each can live in its own class, neatly separated and still be triggered in the same way. Now let's look at the invoker in our system. Here is a class called gamepad. This is the only part of codebase that directly responds to input, but it doesn't need to know what any command actually does. It keeps a dictionary that maps keyboard keys to commands. When we call set command, we bind the key to a behavior like jump, attack, or dash. In execute command, we check if the key is bound. If it is, we execute the command, then store it in a history list. This gives us a nice benefit. We can add a replay method that replays all stored commands in order. Imagine this for replays, tutorials, or even debugging player input. Then we have combo support. The method setCombo allows us to define a sequence of commands, say jump, attack, attack, and associate it with a special combo move. Let's break down check combo pattern. This method checks whether the most recent commands match the combo pattern we define. It does this by slicing the end of the history list using skip and comparing it to our stored pattern using sequence equal. If the sequence matches exactly in both order and content, we execute the combo command, and just like that, we've added reactive combo logic. Because everything here works with iCommand, the invoker stays fully generic. It doesn't care if command plays an animation, triggers VFX, or sends a network packet. It just runs it. Now we bring everything together in the gamepad mapper mono behavior. This is what sits in your Unity scene and connects real-world input to the command system we've built. At the top, we serialize a reference to a VFX for combos. Then we get a reference to our animation manager, which will handle playing all our animations. In a start, we create a new gamepad, that's our invoker, and call configure commands to bind keys to actions. In update, we listen to 3 keys, space triggering a jump, return triggering an attack, and R replays the full history of commands. Each call delegates to the gamepad, which handles execution, history, and combo logic under the hood. Inside configure commands, we create command instances, jump, attack, and a combo command that includes VFX. Then we bind these to keys using set command. Finally, we define a combo pattern, jump, attack, attack, and tell the gamepad what to do if it sees that pattern. Trigger the combo command, that's it. Let's switch to Unity Editor, attach the gamepad mapper script to a game object, hit play and test everything we've wired up in action. In play mode, press jump to trigger the jump animation, or return to perform an attack. Then try the full combo, jump, attack, attack, and watch the combo action complete with visual effect come to life. And finally, press R to replay the entire sequence. What we now have is a complete, extensible, and decoupled input system, capable of handling single actions, replays, and combo detection, all with clear, isolated logic and no hard-coded conditionals.